Streamed in a long time. We're doing a book called Mathematics in Lean. I want to do more formal mathematics. More specifically, there's this book, Ideals, Varieties, and Algorithms, and I want to prove or do something with Grosvenor bases, and I want to learn that. But I want to do all the exercises in the book formally because I feel like then it'll be easier for me to work on my own and actually know that the proofs are right. So I've already done a number of this, but I feel like I wasn't taking it seriously. I feel like on stream I'll take it more seriously. Okay. The goal of this book is to teach you to formalize mathematics using the Lean4 interactive proof assistant. It assumes that you know some mathematics but does not require much. Test. Maybe I'll turn it down just a little bit. Okay. Although we will cover examples ranging from number theory to measure theory and analysis, we will focus on elementary aspects of those fields in the hopes that if they are not familiar to you, you can pick them up as you go. We don't presuppose any background with formal methods. Formalization can be seen as a kind of computer programming. We will write mathematical functions, theorems, and proofs in a regimented language like a programming language that Lean can understand. In return, Lean provides feedback and information, interprets expressions, and guarantees that they're well formed. Ultimately certifies the correctness of our proofs. Okay, so then it just goes through how to use the fucking extension and all that. Okay. We intend for you to work on the exercises. The text will often include examples like eval hello world. Let's see, what is the docstring for eval? Let's see. Does it? Oh wait, you know what? I might need to do this. I thought I would get okay. Sorry, I had to fix that stupid. For some reason, the GitHub Copilot thing made control/ not comment out things. All right. Put simply, Lean is a tool for building complex expressions in a formal language known as the dependent type theory. Every expression has a type, and you can use check to print it. Some expressions have type n or n to n. These are mathematical objects. We'll just, is there a way to hide this thing? Whatever, I'll just get used to it. Okay. Okay, so check. Oh, wait. We need to delete this. Okay, so it takes a bit because it needs to import all of this, and it takes a while. All right, so we can see 2 plus 2 is of type n. This function is probably n to n. There we go. Okay, some expressions have type prop for proposition. These are mathematical statements, like the equality of 2 plus 2 equal to 4. You can check this, but it doesn't actually say whether or not it's true. It says it's a proposition. So this is not a proof of it being true. Now, here's a more interesting proposition. For all x, y, z, and n natural numbers, where n is greater than 2, and x times y times z is not 0, meaning none of these elements are 0, then it implies that x to the n plus y to the n is not equal to z to the n. So there does not exist some combination of these where n is greater than 2 and none of them are 0. So You can check this. This is also just of type prop. So it's the exact same type as 2 plus 2 equal to 4. Now here is a proof. Here's a proof of 2 plus 2 equals 4. And this, let's see what it says about RFL. Some expressions have a type P, where P itself is of type has type prop. So if you check easy, easy is of type 2 plus 2 equal to 4, which is a proposition. Okay. Such an expression is a proof of the proposition P. If you manage to construct an expression of type Fermat-Last theorem and Lean accepts it as a term of that type, you've done something very... Okay, so let's deconstruct that. If you manage to construct an expression of type Fermat-Last theorem and Lean accepts it as a term of that type, then you've done something very impressive. Using sorry is cheating, and Lean knows it. So now you know the game. All that is left to learn are the rules. Very cool. This book is complementary to a companion tutorial called Theorem Proving in Lean, which provides a more thorough introduction to the underlying logical framework and core syntax of Lean. Theorem Proving in Lean is for people who prefer to read a user manual cover to cover before using a new dishwasher. If you're the kind of person who prefers to hit the start button and figure out how to activate the pot scrubber feature later, it makes more sense to start here and refer back to Theorem Proving in Lean as necessary. Another thing that distinguishes mathematics in Lean from Theorem Proving in Lean is that here we place a much greater emphasis on the use of tactics. Given that we are trying to build complex expressions, Lean offers two ways of going about it. We can write down the expressions themselves, or we can provide Lean with instructions as to how to construct them. For example, the following expression represents a proof that of the fact that if n is even, then so is m times n. So for all natural numbers m and n, even n implies even m times n. Okay, so what's happening here, I still get confused by this syntax. Basically, basically by the definition of even n, you're able to take n equal to k, some k plus k. I don't really get these angled brackets or whatever. But then what you do is you substitute n equal to k plus k in the expression of in the expression of m times n. So then you say m times n is equal to m times k plus m times k. So before we just rewrite hk and we have m times k plus k is equal to, and then to justify that, mol add means the left distributivity of times over plus. So then you get to this equality. And so then we're good, and we have a proof of this hypothesis that m times n is equal to m times k plus m times k. Now, I don't exactly know how this works. I feel like it used to show me a doc string for the tactic. I don't know why it's not doing that anymore. But anyways, then you basically take L to be M times K. The proof term can be compressed to a single line. A function of... I don't really get these angle brackets, but they don't really explain it. The following is instead a tactic style proof of the same theorem, where theorems starting with comments or commas, or whatever. Dashes. Okay, so let's walk through this one. So it's the same statement of proof, and we can see that if I highlight this. Interestingly, what is different about this one? Oh, it's just the use of N versus nat. I think N and nat are the same. Okay, so R intro MNHK. What does that do? That gives us... And if we hover over even... Okay. An element of A of a type alpha with addition satisfies even A if A equals R plus R for some R in alpha, or of type alpha. So then we get, basically, we expanded out that K is the R in that case, and then HK is that hypothesis that by definition is true. So we get that as part of our toolkit, I guess. We need to prove M times N is twice a natural number. So we need to prove M times N is twice a natural number. Let's show it's twice M times K. Okay, so then you rewrite the hypothesis for the left-hand side of the equality you're trying to prove, and then you use this ring tactic that proves the rest of it. And ring just basically says that it does all it can to figure out this, how to rearrange this so that it works. As you enter each line of such a proof in VS Code, Lean displays the proof state in a separate window, telling you what facts you have already established and what tasks remain to prove your theorem. You can replay the proof by stepping through the lines, since Lean will continue to show you the state of the proof at the point where the cursor is. In this example, you'll see that the first line of the proof introduces M and N. We could have renamed them. And also decomposes the hypothesis even N to a K and the assumption that N equals 2 times K. Or really K plus K, but whatever. The second line, use M times K, declares that we are going to show that M times N is even by showing that M times N is equal to 2 times M times K. The next line uses the rewrite tactic to replace N by 2 times K in the goal, and the ring tactic solves the resulting goal, that. The ability to build a proof in small steps with incremental feedback is extremely powerful. For that reason, tactic proofs are often easier and quicker to write than proof terms. Yeah, the proof terms, dude. I don't really get that. There isn't a sharp distinction between the two. Tactic proofs can be inserted in proof terms, as we did with the phrase by rewrite HK mul left com in the above example. I don't think that was anywhere actually, but whatever. We will also see that conversely, it is often useful to insert a short proof term in the middle of a tactic proof. That said, in this book, our emphasis will be on the use of tactics. In our example, the tactic proof can also be reduced to a one-liner. Yeah, just with semicolons. Same thing. Here, we have used tactics to carry out small proof steps, but they can also provide substantial automation and justify longer calculations and bigger inferential steps. For example, we can invoke Lean's simplifier with specific rules for simplifying statements about parity to prove our theorem automatically. Let's see, if I hover over that, does it give me anything about that? Not really. Another big difference between the two introductions depends only on core Lean and its built-in tactics, whereas mathematics in Lean is built on top of Lean's powerful and ever-growing library, MathLib. As a result, we can show you how to use some of the mathematical objects and theorems in the library and some of the very useful tactics. This book is not meant to be a complete overview. Rather, our goal is to introduce you to the style of thinking that underlies that formalization and point out basic entry points so that you are comfortable browsing the library and finding things on your own. Interactive theorem proving can be frustrated and the learning curve is steep, but the Lean community... Okay, blah, blah, blah. Okay. Basics. This chapter is designed to introduce you to the nuts and bolts of mathematical reasoning in Lean, calculating, applying lemmas and theorems, and reasoning about generic structures. We generally learn to carry out mathematical calculations without thinking of them as proofs. But when we justify each step in a calculation, as Lean requires us to do, the net result is a proof that the left-hand side of the calculation is equal to the right-hand side. In Lean, stating a theorem is tantamount to stating a goal, namely the goal of proving the theorem. Lean provides the rewriting tactic RW to replace the left-hand side of an identity by the right-hand side in the goal. If a, b, and c are real numbers, mul assoc a, b, c is the identity a times b times c is equal to a times b times c. And mul com a, b is the identity a times b is equal to b times a. Lean provides automation that generally eliminates the need to refer the facts like these explicitly, but they are useful for the purposes of illustration. In Lean, multiplication associates to the left. So the left-hand side of mul assoc could be also written a times b times c. However, it's generally good style to be mindful of Lean's notational conventions and leave out parentheses when Lean does. Okay, so we want a proof that this is true. Hold on, I'm going to switch my pants. I'm hot. Okay. Test. No drop frames. Okay, I think we're good. All right. So let's start here. We have 3 real numbers, and we have, hold on. The background removal actually is pretty good. I'm very surprised. Test? All right, what about now? There we go. So the first thing we're going to do is swap A and B. So that's what molcom AB does. Then we're going to do mol soak, and we're good. That's easy. The import lines at the beginning of the associated examples file import the theory of the real numbers from MATLAB, as well as useful automation. For the sake of brevity, we generally suppress information like this in the textbook. Okay, whatever. You're welcome to make changes to see what happens. You can type the R character. Okay. The symbol doesn't appear until you hit the space or tab. You hover over a symbol when reading a lean file. We'll show you the syntax. Okay. I want to try to state that. I did this last time and I don't understand what is wrong. I type sorry here. Okay, we're good. Okay. So, um, this is true, but I have no idea how to do it. Okay, wait. First, let's do this. Oh. Can I do that? So then we want to do that R cases thing. No, no, no. What did we do earlier? We used this syntax here. Why do I need to get rid of the by? All right, let's try the other way. I like the tactic. Our case. Oh wait, what was it? Intro. Our intro. K H H K. What's wrong? What's wrong? What's wrong with this? Wait, can't I just say this? So use is a great tactic. But I want to know how to rewrite that hypothesis. How do I get that hypothesis? Oh, that's how we get it. I forgot. I have to. Oh, okay. Yeah. Or whatever. Why is it going? Can I just say rewrite even? Yeah, use one works, but use is like too much automation for me. I want to rewrite the. Can you just do this? Oh, wait, what was that? Oh, that did work. And then I probably can still. Let's see. Does that work? Oh, interesting. Okay. So we can do this. We can do use one. Okay, so those are two proofs. This is used to okay. All right, I don't know how to do this one. Do later. All right, so now we have more. Am I using the right? I already did all these things. You know what I'm gonna do? I made a copy of this. So let's just go down to here, and we're gonna go back to okay. All right, so we have some of our own to do. Let's do this. All right, so this is pretty simple stuff, I think. So first, mol com. I guess we got to do CB. Okay, then we want to do rewrite mol assoc BCA. Then we want to rewrite mol com CA. And then we're good. So that's it. That's the solution of that one. All right, now what about this one? We have ABC, A times B times C, and B times A times C. All right, so first off, molcom BC. Oh, wait, actually? Can I just do this? Will it figure it out? Oh, wait, I have to do this, right? Does it tell me that I am allowed to do that yet? Okay. Yeah, I didn't fully walk through this. I stated this problem because I wanted to prove it, but I don't think it's going to work. Okay. Okay, so what is the name of that symbol? Entails. Okay, so sometimes people say target for just the thing and sometimes goal for both. Okay, whatever. Try proving these identities, in each case replacing sorry with a tactic proof using rewrite. You can use, yeah, okay, so we're allowed to use this. /L to reverse an identity. So left molassoc ABC replaces A times B times C with the parentheses. Note that the left pointing arrow refers to going from right to left in the identity provided by molassoc. So if we hover over molassoc, just hover over it, we see here this. And so instead of going this way to the right, we go to the left. Makes sense. And if you alt click this, you can actually see the proof. Okay, let's keep going. So we are allowed to use this, but I have to do. Nice. Oh yeah, you don't have to provide the arguments. Oh, that's faster. Cool. And this one with only one argument. Let's see, what does it say about that? Okay, cool. Okay, so what are we doing here? We have A times B times C. All right, so oh, okay, we did it. A, B, E. Okay, wait, where are we at the beginning? So if I rewrite this, what this will do is replace E with F. So this turned into F. I think it highlights it, right? Yeah, it highlights it. Okay, that proof makes sense. Okay, what's next? So we gotta do our own. All right, that's easy. All right, so what I'm gonna do right now, rewrite mol assoc. Okay, oh. See how to do that. Now we want, there we go. Then we want to rewrite H. Then we want to do, all right, that was easy. So we added these parentheses so that it was one term that matched this thing. Because if we comment this out, I think that this will say failed to, yeah, tactic rewrite failed. Because it didn't find B times C, even though it's like kind of obvious it's in there. Like that's one thing that is just really generally annoying about these dealing with expressions is that there's this implicit parentheses, which makes it easier to read, but it's also really annoying. So, anyways, you have to do the Molassoc first. All right, so we got another one here. So we want to prove that C equals 0. And I feel like we can just rewrite hype. Oh, wait, we can rewrite hype at hype like that or something. What is it? We got to read this one. Oh, wait. Sub self. Okay, I'm going to try writing sub self. Let's see, what does this even mean? A minus A. Okay, so first. Wait, did I skip ahead? What happened? Skipped way ahead. Okay. Okay, we could rewrite hype. Okay, I get it. Rewrite hype. Okay, then we want to rewrite. Oh, wait, I think I can do this all in one line. Okay, cool. So then we want to do mul com. Okay, then sub self. All right, that was it. That's easy. Yeah, but I feel like there probably is a way to go the other way where you use one hypothesis to substitute. That's almost certainly exists. I just don't know what to do, how to do it. Is this the same proof? What is this? Didn't we just do this one? Oh yeah, it's just saying that you can list them in a list or whatever. And you can still see the incremental progress by placing the cursor after a comma. Okay. Another trick is that we can declare variables once and for all outside an example or theorem. Yeah, that's nice. Inspection of the tactic state at the beginning of the above proof reveals that lean indeed included all variables. We can delimit the scope of the declaration by putting it in a section end block. Finally, recall from the introduction that lean provides us with a command to determine the type of an expression. Okay, so we're going to just walk through those. We got to zoom through this because I already did all this shit. I'm just reviewing. All right, so check A, it's going to be real. Check A plus B, that's also real. Check A of type R, that's going to be a proposition? No. It's not a proposition. I think it's the exact same as this. It's just you are certifying. Okay, this is going to be a type of equality or something. Yeah, it's a type of prop. And this is a proposition. So if I did this, check this, it would be of type prop. Yeah. Okay, so this is a proposition. This is what they were saying earlier, is that the this is a type P, and P is a prop. Okay. What is this one? This is probably the same thing. Yeah, that's the same thing. And then this is sort of the same thing. Molcom A. And then this is interesting because it's quantified overall. And then Molcom, it's probably quantified over both. It doesn't actually say. It's even more general because it doesn't even it just specifies the most basic algebraic structure in which the commutativity holds. And there's a name for that. It's a magma, commutative magma. What the fuck is going on here? Okay. All right. The check command works for both objects and facts. The command check A of type R states our expectation that A is R. So wait, so let's just try switching that to n. Yeah, I remember this. There's an upcast. Okay. I bet this whole thing. Ring. That's so awesome. I wonder how that works. I probably could dive in and figure out how ring works at some point. That'd be interesting. I wonder if it tries to do like it takes both terms and does a canonicalization procedure that presumably there's one form that you can arrive at and then just check their equality. I don't know how if that's how it works, but that would be how I think it's done. Do I really want to walk through this boring ass proof? Let's see. Let's try some more examples. The theorem 2 mole A says that 2 times A is equal to A plus A. The theorems add mole and mole add express the distributivity of multiplication over addition, and the theorem add assoc expresses the associativity of addition. Okay. Mole add mole, add mole. What does that get us? So here, right. And then it's just more rearranging and more rearranging. Oh, yeah. Okay, this calc thing. I don't really like the calc tactic. It does make it easier to read, but it's also kind of a boring exercise. Maybe I'll skip that. Pow. Pow wow. Okay, fine. Let's just bang this out. All right, so rewrite add mol. Where are we at here? I should be able to do mol add, right? You guys, today I went to the dispensary and I parked in the wrong parking lot, and these assholes put like a sticker on my car. Totally ridiculous. I mean, it's like they're right, but also like chill out. I'm gonna be there for like 2 minutes. It was like a bunch of spots. If it was whatever. 8 times C plus 8 times V. I wish there was just a collect tactic. Whatever. Could I just do um Oh, wait, sorry. I'm dumb as hell. Okay, we're good. Rewrite. Let's just try this. Ring. Easy. Ring. All right, so uh uh add mul mul sub mul sub. A times A times B times A. Yeah, mul com BA. Uh uh add sub. What is add sub? Sub self. Or wait. Oh, that's annoying. Sub. Okay, wait, hold on. Is there a way to repeatedly apply? Because I want to do left to mul. Oh, wait. This is the other way around. No, what? Wait. To. No, pow 2. That's what I want. Can I give it a star? For whatever. Okay, now minus add sub. Is there a sub add? Add mul. What is add mul? Yeah, add mul is the classic, what I expected. Add sub. Oh, wait, can I do this? Damn, I really fucked this one up. I bet I could just do this too. Ring. Easy AF. Okay, what's the solution? I don't want to sit around just doing something that's so obvious. Calculating. Wait. Wait, which one am I in? I'm in calculating. I'm trying to prove. No, I already did all these. Wait, what? A plus B times A minus B. Bam? There's no solution to this one? Come on, man. Sub. It's gotta be that I fucked this up. Okay, where are we at right now? Wait, what if I did this? What do I want to do? I want a squared minus a times b plus a times b. Okay, wait, let's read these again. This one's obvious. Mol sub is fine. Let's try it again. I'm going to try it again. I'm going to do this. Rewrite mol sub. Mol sub. Mol add. Or no. Add mol. Add mol. Okay, then we have the a times a. Okay, yeah. See, that's how you're supposed to do it because I want to skip these so that. Okay, then which is the one that gets rid of the? It's oh wait, we can do sub, right? But it's left. Okay, then rewrite mol com BA sub self. What? Oh wait. Oh wait, is that gonna work? Oh wait, we can do add sub. Fuck. Here we go. Okay, then we can do sub self. We can do add 0, and we're good. Hell yeah, brother. Okay, cool. That's a lot of random rewriting shit. That's not even in the solution, man. Can make a PR to do it. This is in section what? Calculating, right? Is it the last one? Oh, here's what it was. Yeah, you can rewrite add a hypothesis. Okay, wait. I want to add this. I think. All right, let's look at the solutions thing. Is that. Wait, none of these are in there. This one's not in there either. Fuck. All right, so do we have to do those too? Whatever, I'm just going to add this. Okay. We can get rid of all this. All right. So now we're following exercise is more challenging. We can also perform rewriting in an assumption in the context with at. Rewrite at hypothesis. Should we walk through this one? Whatever, I think we get it. And the exact. All right, we'll do it just for exact. All right, so what did we do? So we had the hypothesis that C is equal to D times A plus B. So we rewrite this guy with oh no, we rewrite hype with this one. So B, so it's going to be C is equal to D times A plus A times D. Okay. Then mole com, yeah, that makes sense. Then 2 mole. And we're trying to prove that C is equal to 2 times A times D, given these assumptions. Okay, then you do mole asoc, and then your exact. Yeah, okay, cool. And exact is just saying that, look, we have a hypothesis that literally matches the thing that you're trying to prove. So then we're good. Okay, and then it just shows that Ring does all this automation for us, especially this one, which is a total pain in the ass to figure out. Okay, what's next? Did you even need to do that? What happens if you do this? Okay, whatever. This really doesn't figure that out? Oh, I see. It doesn't actually do those. Okay, that makes sense. But once it's in the format of Ring stuff. The Ring tactic is imported indirectly when we import MATLAB data real basic, but we will see in the next section that it can be used for calculations on structure other than the real number. It can be imported explicitly with the command import matlab.tactic. Okay, there's a variation of rewrite called nth rewrite, which allows you to replace only a particular instances of an expression in the goal. Cool, that's neat. It's useful. Okay, proving identities in algebraic structures. Mathematically, a ring is a collection of objects, R, operations plus and times, and constants 0 and 1, and an operation x to minus x such that R with plus is an abelian group, with 0 as the additive identity and negation as the inverse. Multiplication is associative with identity 1, and multiplication distributes over addition. Okay, now we know what a ring is. Big deal. Big freaking deal, man. In Lean, the collection of objects is represented as a type, R. The ring axioms are as follows. Okay, should we read all these? I feel like we don't need to. What's the big deal, man? All right. You will learn more about the square brackets in the first line later, but for the time being, suffice it to say that the declaration gives us a type, R, and a ring structure on R. Lean then allows us to use generic ring notation with elements of R and to make use of a library of theorems about rings. The names of some of the theorems should look familiar. They're exactly the ones we used to calculate with real numbers in the last section. Lean is good not only for proving things about concrete mathematical structures like the natural numbers and the integers, but also for proving things about abstract structures characterized axiomatically, like rings. Moreover, Lean supports generic reasoning about both abstract and concrete structures and can be trained to recognize appropriate instances. So, any theorem about rings can be applied to concrete rings like the integers, the rational numbers, or the complex numbers. It can also be applied to any instance of an abstract structure that extends ring, such as an ordered ring or a field. Not all important properties of the real numbers hold in an arbitrary ring, however. For example, multiplication on the real numbers is commutative, but that does not hold in general. If you have taken a course in linear algebra, you recognize for every n, the n by n matrices of real numbers form a ring in which commutativity usually fails. If we declare R to be a commutative ring, when we say commutative, because is there a ring where the plus operation is non-commutative either? Because this says that abelian group, I'm pretty sure, means commutative group. Okay. If we declare R to be a commutative ring, in fact, all of the theorems in the last section continue to hold when we replace R by R. Pretty cool. We leave it to you to check that all the other proofs go through unchanged. Notice that when a proof is short, like by ring or by linear arithmetic or by sorry, it is common and permissible to put it on the same line as the by. Okay, whatever. The goal of this section is to strengthen the skills you've developed in the last section and apply them to reasoning axiomatically about rings. We will start with the axioms listed above and use them to derive other facts. Most of the facts we prove are already in MATLib. We will give the versions we prove the same names to help you learn the contents of the library as well as the naming conventions. Lean provides an organizational mechanism similar to those used in programming languages. When a definition or theorem foo is introduced into a namespace bar, its full name is bar.boo. Wait, bar.foo, bro. The command open bar later opens the namespace, which allows us to use the shorter name. Okay. The next example shows that we do not need add 0 or add right neg. Because they follow from the other axioms. Okay, let's walk through this. So now we're no longer here. We are... Okay. Does it do it all over again? Oh no, at least it remembers it. Okay. I think I'm gonna get some fruit. Okay. Yeah, because it's interesting because there are terms that are just taken definitionally or axiomatically, like Molcom in the rings. You just accept it. Right. You know, I'm curious. I want to see what happens if I do. I'm gonna comment this out. I'm gonna do rewrite. I'm gonna say ring dot add 0. Nope. Oh shit. Wait, what was it? It was. There we go. Oh, but it restarted the thing. That's really annoying. Hmm. Okay. Well, there probably is a way to just do it. Oh yeah. Oh, that's just showing the. Okay, whatever. Do I do this? Rewrite. Um. Wait. So we want to get into that form. So we want to do. I'm pretty sure that's the one. Yeah, that's the one we want to do. Add left neg. So we want to do add a soak. Okay. Then we want to do add com b. Then we want to do add left neg. Oh, we could probably use but you know what? It's probably better to only use the axioms. I mean, what's the difference? It's the same, but I guess for the exercise, maybe it's okay. And then add 0. Yeah, that's fine. Okay, cool. Add left cancel. Can I do this? Uh, does that do anything? Did not find it. Oh, interesting. Oh. Okay, all right. Yeah, that's why Copilot recommended me this add 0 thing. Wait, that's interesting. I didn't find that thing. Okay, but then you do this thing. I think if I give it A, I think the way you do this is you exact H. Or maybe you rewrite. Yeah, okay, so let's do this. Uh, um, can I do add com? Does that work? Wait, what? Why can't I do that? All right, wait, I just want to try B. Okay. All right, I'm gonna do add a soak. That didn't work. Okay, then I want to do rewrite H. Okay, so this is kind of like a wonky. And then add neg cancel, right? Can I do that? Oh wait, you know what? I think that's it. All right, cool. Right, add left cancel, add right cancel. Did they say something about not being able to use? With enough planning, you can do each of them with 3 rewrites. I feel like that's using this one. But you know what? We're here to prove them. All right, let's try to write these. And I want to do rewrite, add com, A add com C, add H. Right, okay. I can't do this? Rewrite add left cancel H. I'm confused why I don't need to exact H. Okay. Oh, this is a good one because it's not an axiom. That mole 0 equals 0. Okay. I should leave that in. Okay. All right. So you have more slack. It's not gonna work out. Okay. Dude, I hate this thing. These chargers that think it's a good idea to do this thing where you have like the brick, the transformer or whatever it's called, should be connected to the wall. That's clearly the better design. Okay, give me a second. Okay. Okay. We will now explain the use of the curly braces. Imagine you are in a situation where you have A, B, and C in your context, as well as the hypothesis H, A, B, A plus B is equal to A plus C. Now you would like to draw the conclusion B equals C. In Lean, you can apply a theorem to a hypothesis and facts just the same way you can apply them to objects. So you might think that add left cancel A, B, C, H is a proof of the fact, but notice that explicitly writing A, B, and C is redundant because H. Okay, so implicit arguments are when curlies. So after that, we have H. Wait, what? Okay, that one's a little strange, but I get it. We have used a new trick. If you step through the proof, you can see what's going on. The have tactic introduces a new goal with the same context as the original goal. The fact that the next line is indented indicates that Aline is expecting a block of tactics that serve to prove the new goal. The indentation therefore promotes a modular style of proof. The indented subproof establishes the goal that was introduced by the have. After that, we are back to proving the original goal, except a new hypothesis H has been added. Having proved it, we are now free to use it. At this point, the goal is exactly the result of add left cancel H. We could equally well have closed the proof with apply add left cancel H, or exact add left cancel H. The exact tactic takes as argument a proof term which completely proves the current goal without creating any new goal. The apply is a variant whose argument is not necessarily a complete proof. The missing pieces are either inferred automatically by Lean or become new goals to prove. Oh yeah, right. I remember this. I did this a couple of days ago, and I was confused by it. I don't get why it's not add right cancel. Should be add right cancel. Right? Because oh wait, there's something weird going on. Oh no, it is on the left. Just getting all tripped up by the yeah. Ooh, sorry. Probably pretty loud. All right, that one was. This is probably not optimal, but we did it. It's weird that you can't. Does that work? I guess you don't need the add 0. Yeah, it's totally redundant. Cool. Can you rewrite this as ecom or something? Easy, son. Easy. Alright, so we have neg eq of add eq 0. No, because we have right. Okay. Wait. That seems weird. But a is minus 0. That seems wrong. I mean, it's probably right, but I don't get it. Okay. Let's get back to it. So neg neg. Neg neg. What do we do here? What do we have? You know what? I want to try this thing. I love this thing. That's stupid. This doesn't. Wait, it did it. But I don't get why it did it. Okay, we have up here, we have something of the type minus a is equal to a. So then eq neg of add eq 0 is of the form, if you have h of type a plus b equals 0, then minus a equals b. But I don't know why you're even allowed to, like, I want to try this. Does that work? Oh my god. Look at that friggin' thing. Well, you can provide that, right? But that didn't do what I wanted. Right, because what I think I was hoping for is that by going the other way and giving it something of this form, that I could rewrite it as, so in this case, yeah, a is to minus a and b is equal to a. It's very confusing. But anyways, that would give me minus a plus b equals 0, which would be minus a plus a equals 0, which in that case we could use probably neg add. Oh, yeah, it's probably not neg add. What is it called? Right, add right neg. Right. So that's what I was hoping for. But that obviously didn't do what I wanted. But then what? So, okay. But what I don't understand is how apply is using this to get what? So apply is smart enough to go the other way somehow, but doing rewrite left or left rewrite didn't. I don't know why. I'm gonna add a comment. I don't really understand why. Ooh, that's not really. I want to try that again. Hmm. But it's left. Why doesn't that change? Okay, whatever. But apply is able to get the a plus b equals to 0 form from minus a equals a. Or wait. But anyway, so we get this, and then we can just do. Well, I want to try rewrite again, but it's gonna be add left neg, and then we're good. We could probably also just write apply add left neg. Oh, okay, it's the same thing. Yeah, I don't really get this part. Because you go from okay. Okay. So I feel like that was a good one. In lean, subtraction in a ring is provably equal to addition of the additive inverse. Cool. That's a good theorem to know. Sub eq add neg. On the real numbers, it's defined that way. Notice the lack of by. The proof term reflexive is short for reflexivity. Presenting it as a proof of a minus b is equal to a plus minus b forces Lean to unfold the definition and recognize that both sides as being the same. The RFL tactic does the same. This is not an instance of what is known. This is an instance of what is known as a definitional equality in Lean's underlying logic. This means that not only can one rewrite sub eq ad neg to replace a minus b with a plus minus b, but in some contexts, when dealing with the real numbers, you can use the two sides of the equation interchangeably. For example, you now have enough information to prove the theorem sub self from the last section. Oh, yeah. Sorry. Show that you can prove this using rewrite. But if you replace the arbitrary ring R with the real numbers, you can also prove it using apply or exact. Lean knows that 1 plus 1 equals 2 holds in any ring. That's so weird to me because, like, what does 2 mean? Like, let's say you have a ring of something real weird. Like, I don't know, like a ring of graphs or something weird. I don't know if that's possible, but it's just interesting that 2 exists in all rings. One existing is more of like a hijack of symbols, I feel like, but I don't know. All right, let's do 2 more. Oh, yeah, okay. Okay, why did one mole do both of them? There's 2 here. What is that? Wait, that's super weird. It said it starts at. What? Is it some weird associativity thing or something? No, because this is. Dude, what? That is so bizarre. Oh, you know what it. Oh, no, it did the first one. And if we duplicate this again. Okay. That is really strange. Okay. Well, in any case, let's keep going. All right. We close this section by noting that some of the facts about addition and negation that we have established above do not need the full strength of the ring axioms or even commutativity of addition. The weaker notion of a group can be axiomatized as follows. Additive group A. Add a soak, zero add, and add left neg. That's all you need for additive group? Pretty cool. Pretty cool. Add group has add a soak, the zero add left. How did we approve? Did we approve add zero without using any other things? Like, you must be able to prove add zero in additive groups. Let's look at that. It's very interesting because you go to this mole thing and they have generalized it so that 1 times 1 is the same as plus 0. That's very cool. But I just want to see the proof of it. Let's look at what we did up above. Add 0. Add 0. See, we used, but wait, but we don't have that. We can't just do that. Maybe it's actually just like not true. No, it's got to be true. How how would that work if it wasn't? Okay. How can I prove add 0 in a look at this stupid proof. This doesn't gives up at the actual part. Wait, is there inverses? Oh yeah. All right, start with 0 plus a equals a, which is true by the zero add axiom. Add a inverse to both sides of the equation from the left. Okay, so we have 0 plus a equals a. Want to prove a plus 0 equals a in additive group. Okay, so then we do minus a plus 0 plus a is equal to minus a plus a. The equation of balance due to the group's properties. By associativity, we can change it around. So minus a plus 0 plus a is equal to minus a plus a. Okay, 0 add, so then minus a plus a is equal to minus a plus a. Wait, what the hell? What? This proof is total nonsense. What the fuck is this? This isn't right at all. You know what? I'm going to take it to be true. It's got to be true. What do? You do. Okay, so we have. Okay, so let's just write this out. Can I do this thing? Oh, wait, hold on. I'll just do this. What's wrong? Huh? So we can get rid of this section. Okay. Oh, I guess I get it. Namespace is a named section or something. Whatever. Example. Oh, wait. Let's just do this. Add 0. A plus 0 equals a. We don't have this. Let's see. Hopefully it says Okay, cool. Failed to synthesize. Add commutative magma because it's not. It's not. We don't get to say that. It's not allowed. So what can we do? Presumably we can do this. There's only a couple of options. Oh. We don't have right. You know, I'm going to use that. Okay. All right, so I've proven it to myself. The only thing that's sus is this one, but it's a similar thing of just like doing it. Did we do add right neg? See, add right neg uses the commutativity. We don't want that. There has to be another way to do this. Okay, I think we can probably just do this. Flip it around. Oh wait. A plus minus A. Hold on. Add right neg is minus A plus A is equal to 0, A in A of type G. That's what it is. Oh wait, no, it's the other way around. Plus minus. Okay. So now how do you prove it? Yeah. Oh, you know what? Wait, but I want to do it on the. I'm gonna do it on the left side. Uh. Can I do it again? Oh, wait. Am I... dumb? Is it not just... I don't think I can just do... I don't think I can just invert it. That's totally void. Oh, I think... Could I do this? Wait, but that doesn't add it to the right side. Damn. Son. Damn, dude. How do you do this? Why am I so dumb at this? I don't know. Help me prove add right egg in add group. Outline. This is such a fucking cop out, dude. What a dipshit, man. All right, let's keep going. Let's keep going. I'm gonna skip that. I know it's true. Mm. Oh shit! Yeah. See, this is what I was going down the road of. All right, whatever. I look outside and see all these things. I mean, I was basically doing exactly what this exercise is. This is tough though. Mole right inv is the one that I got stuck on. Add 0 is the same as mole 1. And this I can probably just basically copy over. Mole in rev? I don't know what that is. This is that one looks hard because that one looks like a real derivation. It's not just like a commutative thing. It's like a real sort of new thing. Basically, what it's saying is that we have minus a plus b is equal to minus a plus minus b. It's equal to minus a minus b. Whatever. So fuck, I don't like this. I want to go home. This is a tough one. I'll look inside and see how. Okay, so we're trying to prove. I don't like this. I don't like this syntax with mole and inverse. I'd rather use minuses. So we're gonna do a uh plus minus a is equal to 0. It's the same thing. And what we have is and we have 1. This is add soak. We have 2 uh 0 add, which is 0 plus a is equal to a. Then we have 3, which is minus a plus a is equal to 0. Okay, so I got stuck on the first one. I kind of want to look at the answer, but I feel like maybe I should try it. So what we want to prove is I'm going to prove a plus minus a equal to 0. Fuck it. I spent long enough thinking about this one. Okay. All right, so what do we... All right. So have H A times A inverse times A times A inverse times A times A inverse. God, I hate this syntax. So confusing. So what would this be in add? It would be A plus minus A equals 0, and H would be A plus minus A minus, so plus A plus minus A plus A plus minus A. Okay, so let me just write that out. So we'd have, it would be minus A plus minus A plus A plus minus A plus okay, so then they do a soak. Wait, what changed? What do we get here? Mole left inverse is the same as add left neg. Okay. Wait till we're right here. Okay, so then we get a 1. Then we have 1 mole, which is the same as add 0. Okay. And then mole left inverse. Right. So now that we have H, we want to rewrite. Wait, what does that do? Cool. That's a crazy proof. That's really good. That's one to review. Where was this put even? I didn't even see that thing. I look outside. Sad is the only thing. Can't feel your pain and I feel alright about it. Can't feel your pain and I feel alright about it. I can't feel your pain and I feel alright about it. I can't feel your pain and I feel alright about it. Wait, what? So then we did this, right? And then we did this. Minus a plus a minus a. Oh, wait. Okay, then we did this. Then we did this. And then we did this. So then that's a proof of H. It's a really interesting, really cool, actually. And so then with H, you rewrite it on the right hand side. Then you just cancel those guys out. And then 1 mole, and then you have the equality. That's really, really cool. Yeah, from the associativity, you get this. Like, it's not commutative, but you have this commutative property of multiplication by 1 or adding by 0. Or rather, the commutativity of multiplying by inverses or adding inverses, or inverses added to. It's all weird symbol manipulation. Okay. And then this one is exactly what I wrote earlier, and I just relied on add right neg because I didn't prove this one. This one is definitely hard for me. I didn't get that one. And now this one is an interesting one because we have a plus b inverse or minus is equal to, oh, and it's actually b minus b plus minus a. You know what's interesting about this one? I might skip this one. This one looks complicated because what's crazy about this is it's minus b times minus a, not, or plus, not a first. I wonder if the other way is true. It probably isn't, right? Because that would be the same as saying, oh, what the? Which, because Yeah, so it's just not true. So that's a really interesting one. Because that would be the same as saying that crazy. Should I walk through this one? I feel like I should keep going. This one's tough. Look at how many rewrites there are. All right, let's keep going. Wait, I want to try. That's sick. I went outside and see all these things. All right, section 2.3, using theorems and lemmas. Rewriting is great for proving equations, but what about other sorts of theorems? For example, how can we prove an inequality, like the fact a plus e to the b m to the b is less than or equal to a plus e to the c holds whenever b is less than or equal to c. We've already seen that theorems can be applied to arguments and hypotheses, and that the apply and exact tactics can be used to solve goals. In this section, we'll make good use of these tools. Consider the library theorems less than or equal to flexive and less than or equal to transitive. All right, so here we can see that a is less than or equal to a for all a, and a less than b, b less than c implies a less than c, or less than or equal to. As we'll explain in more detail in section 3.1, the implicit parentheses in the statements of LE trans associate to the right. So it should be interpreted as a less than b implies. I don't even know how to read these. I really hate these. I'd rather just list them out. It confuses me. The library designers have set the arguments A, B, and C to LE trans implicit, so that Lean will not let you provide them explicitly unless you really insist. Rather, it expects to infer them from the context in which they're being used. For example, when the hypotheses H and H prime are in the context, all of the following will work. Three-hour stream. Let's see, how far did we actually get? We haven't even finished a chapter. We're halfway through a chapter. All right, I'm gonna end it. I'm gonna start the stream up again in a minute, but we're gonna be priming a canvas for painting.